Hello students, in this video we are going to investigate integer exponents and the quotient rule. First we're going to consider the following pattern for raising base 2 to integer exponents. For example, 2 to the third power is 8, 2 squared is 4, 2 to the first power is 2, and following in like fashion, notice each time we're dividing by 2, or you might say multiplying by 1/2, that would suggest that 2 to the 0 power is half of 2, or 1, wouldn't it? And continuing further then, notice how we're reducing our exponents by 1 each time and dividing the result by 2 each time. That would suggest that 2 to the negative 1 is 1 divided by 2, or 1/2, and would also suggest even that 2 to the negative 2 power is 1/2 times 1/2, or a 1/4, and 1/4 is 1 over 2 squared, isn't it? Let's consider another pattern using base 10. 10 to the third is 1,000. Reducing exponents, we could say that 10 squared is 100 and 10 to the first is 10. And notice that we're essentially dividing the result by 10 each time, aren't we? So again, this suggests that some number to the 0 power is 1, doesn't it? Because 1/10 of 10 is 1. So we've seen that following our pattern, 2 to the 0 power is 1, and also 10 to the 0 power is 1, isn't it? I want you to take note of that. Continuing, 10 to the negative 1, if we divide by 10, that would be a 1/10, wouldn't it? And let's go one more. 10 to the negative 2 would be 1/100th, which is a 1 over 10 squared, isn't it? These are nice patterns to help us set up first our zero exponent rule. For any non-zero real number, a to the 0 is equal to 1. In example 1, we'll use that zero exponent rule. 7 to the 0 power is 1. The negative of 7 to the 0 power, be careful here, 7 to the 0 is 1, but we keep that negative symbol out front, don't we? So negative 1 for part B. And in part C, we've got an expression here, x isn't equal to 0, so we know we've got a non-zero base raised to the 0 power, and that is equal to 1. So any non-zero raised to the 0 is 1. The next rule we're going to take a look at is the negative exponent rule. For any non-zero real number n and any integer n, a to the negative n is equal to 1 over a to the n. For example, 3 to the negative 2 power is equivalent to 1 over 3 to the positive 2 power. And we saw this pattern on our previous page. We could also call this 1/9. Now let's use the negative exponent rule. In example 2, we want to simplify by writing with positive exponents. We're going to assume that all variables represent non-zero real numbers. Well, 2 to the negative 3 is 1 over 2 to the third power. One of my students said, cross the line, change the sign, meaning cross the fraction bar line and change the sign. And I thought that was creative. Well, 2 to the third is 8, so we can call this 1/8. In part B, we've got a base 1/7 to the negative 2. Let's say 1 over 1/7 to the positive 2. Let's say 1 over 1/49th. And dividing by a fraction, we multiply by the reciprocal, don't we? So 1 times the reciprocal of that denominator, 49 over 1, is 49 over 1, or we might just say 49. Now, an easier way to look at part B is to just flip that base. 1 over 7 to the negative 2 is 7 over 1 to the positive 2, or 49. Let's do that in part C. 3/2 to the negative 4, that's 2/3 to the positive 4. Okay, so here I'm just flipping that, let's say inverting that fraction, changing the sign of the exponent. And we can think of this as 2 to the 4th over 3 to the 4th. And 2 to the 4th is 16. And 3 to the 4th is 81. In part D, we've got a 2 to the negative 1, which is 1/2, plus 5 to the negative 1, or 1/5. And here we want to add these fractions, and I'm going to get a common denominator of 10. 1/2 times 5 over 5 is 5/10. And 1/5 times 2 over 2 is 2/10. And now we can add those numerators and call this, say, 7/10. In part E, m to the negative 3, well, that's 1 over m to the positive 3. Cross the line, change the sign. And in part F, notice that our base is in the denominator, so it's going to come up to the numerator. If we go through the whole process, that would be 1 over x to the 4th. And dividing by a fraction, we multiply by the reciprocal, so that's a 1 times x to the 4th over 1, or just x to the 4th. But the next time you see one of these and you've got a base to a negative exponent in the denominator, just move it up to the numerator to simplify it. Cross the line, change the sign with those negative exponents. Our next rule we're going to take a look at is changing from negative to positive exponents. For any non-zero real numbers a and b and any integers m and n, the following hold. So if we've got a base to a negative exponent in the numerator, notice how that moves to the denominator, cross the line, change the sign of the exponent to positive. Similarly in the denominator. Okay, move that base to the numerator and change the exponent to a positive. If we've got a fraction raised to a negative exponent, we just basically invert that fraction and change that exponent to a positive exponent. In example 3, simplify by writing with positive exponents. Assume that all variables represent non-zero real numbers. So in part A, okay, that 5 in the numerator is coming to the denominator. Cross the line, change the sign of the exponent. That 3 in the denominator is going to move up to the numerator. Cross the line and change the sign to a positive exponent. And then I'm going to go ahead and evaluate this. 3 cubed is 27 and 5 squared is 25. In part B, be careful here. That's a 4 to the 1st power. Leave it where it sits. In the denominator, we've got a z to the 1st power and leave it alone as well. The x to the negative 5 is going to come below. Change the exponent to positive 5. And the y to the negative 2 is going to move to the numerator where it becomes a y squared. So as we simplify these expressions, one thing that we definitely want to do is convert from negative to positive exponents. Lastly, here in part C, that's an entire fraction raised to the negative 3rd, so I'm going to invert that fraction and write it as 2y to the 3rd over x squared, all raised to the positive 3rd power. I'm going to apply that exponent. We're going to have a 2 cubed times y to the 9th. Remember, power to a power multiply, over x to the 6th, power to a power multiply. And as the last step, I think I'll write that as an 8y to the 9th over x to the 6th and evaluate that 2 to the 3rd power. Our next rule is the quotient rule for exponents. It says that for any non-zero real number a, any integers m and n, the following holds. Here we've got a to the m over a to the n is equal to a to the m minus n. And as an example, we might write 6 to the 5th over 6 to the 3rd. Okay, notice that the bases are the same here, aren't they? Now, disregarding the quotient rule, 6 to the 5th is 6 times itself 5 times. And 6 to the 3rd is 6 times itself 3 times. And if we just divide out our common factors, notice that that leaves a 6 times 6 or 6 squared in the numerator, doesn't it? Now, essentially what the quotient rule indicates is that we can use a shortcut, okay, to divide these like bases by simply subtracting the exponents. Notice that 5 minus 3 is 2, isn't it? So these are rules that provide shortcuts for us, essentially. In example 4, we want to simplify by writing with positive exponents. Assume all variables represent non-zero real numbers. In part A, let's say 4 to the 7 minus 5, which is a 4 squared, and I'm going to go ahead and just call that 16. I generally evaluate the simple ones, okay? And part B, notice that this is similar to part A, except the 4 to the 5th is in the numerator and the 4 to the 7th in the denominator, huh? So now as we use the quotient rule, it's top exponent minus bottom. So that's a 5 minus 7, and in this case, it's 4 to the negative 2, isn't it? In other words, 1 over 4 squared, or you might say 1 over 16 if we evaluate that. In part C, we have x to the negative 6 over x to the negative 12, subtracting exponents. Numerator, negative 6, minus denominator, negative 12. And be careful, that's a minus negative 12, isn't it? Well, minus a negative is a plus. And negative 6 plus 12 is 6. So this simplifies to an x to the 6th power. Lastly, part D. We've got an 8 to the 4th over an 8 to the 5th. We've got m to the 9th over m to the 10th, n to the negative 3 over n squared. So we're going to use the quotient rule 3 times here. All right, 8 to the, okay, let's just go ahead and do this. 4 minus 5 is a negative 1, isn't it? Times m to the 9 minus 10, or negative 1, times n to the, careful here, negative 3 minus 2 is a negative 5. Now, each of these bases has a negative exponent, so they're going to get shifted to the denominator. So we write this as 1 over 8 to the 1st is 8. M to the 1st is m. Notice when those come to the denominator, we change the sign of the exponent, don't we? And that n to the negative 5th, as it comes to the denominator, becomes an n to the positive 5th. 1 over 8 m n to the 5th. And as we summarize our definitions and rules for exponents, here we've got a summary table of all of your rules for exponents that we've learned thus far. So this is a nice page to be able to refer back to, okay? I'm not going to read those to you, just know that you have them at your disposal. In example 5, we're going to simplify. We're going to assume that all variables represent non-zero real numbers, and we're going to use all of the rules that you see above in that table, okay? Now, in part A, 3 to the 4th squared. Power to a power multiply, that becomes 3 to the 8th over 3 to the 3rd. Those bases are the same. So next we use the quotient rule and subtract exponents. 8 minus 3 is 5. And if we wanted to evaluate that, 3 to the 5th is a 243 in its evaluated form. In part B, we've got 4x squared times 4x quantity squared. Okay, so our 4x squared out in front, and then we're going to multiply that by, okay, as we apply that exponent, 4 squared times x squared. Now we'll use our product rule. 4 to the first times 4 squared, adding exponents, is 4 to the third. And x squared times x squared is an x to the fourth. And if you wanted to evaluate 4 to the third, you can definitely do that. We can call this 64x to the fourth in its evaluated form. And lastly, part C. We've got an entire fraction here, all raised to the negative 2 power. So I think I'm going to take that fraction and invert it. Let's write this as 3w to the negative 3 times z over 2w z to the negative 5, and that's all going to be to the positive 2 since we inverted that fraction, right? We took care of that negative symbol on our outer exponent. Now I'm going to apply this exponent to every factor inside. Remember, power to a power, multiply. In the numerator, we've got 3 squared times w to the negative 6 times z squared. In the denominator, that's a 2 squared times w squared times z to the negative 10. Now let's see, we can use our quotient rule, and I'm going to go ahead and evaluate my 3 squared and 2 squared. That's 9/4, isn't it? 9/4. W to the, okay, so we use our quotient rule with like bases, and top exponent minus bottom. Negative 6 minus 2 is negative 8. And then with our factor of z, that's z to the 2 minus a negative 10. And that's a 2 plus 10, isn't it? Or a 12, z to the 12th. And just as a final answer, we want to write this without negative exponents. Okay, the 9 stays in the numerator, z to the 12th stays in the numerator, 4 stays in the denominator, and this w to the negative 8, as it sits, it's in the numerator. We want to push that down to the denominator and change the sign of the exponent to a w to the 8th power. So final answer there, 9z to the 12th over 4w to the 8th. Well, good luck on these that involve the 0 exponent and negative exponents.